So now let's look at a modeling approach for trying to figure out what types of sags a customer may see if there's a fault on the circuit. And let's just focus on doing three-phase voltage faults. If you want to do something more complicated, you could always use windmill for something like that. So what we're going to be assuming in our modeling technique is that we could use a kind of a simple Thevenin equivalent for the power grid. And so what we'll have is we'll have a voltage behind an impedance. I have a Z sub written there, but that's actually a combination of the substation transformer and the transmission system put together. And so typically a utility will have this value available at the substation. Then what you're going to have is you're going to have some location for the fault in the circuit, and we'll have a net line impedance from the substation bus up to that fault. And so in this case, this is shown as Z line default, but this would be a positive sequence impedance where you'd have the line impedance per mile for the overhead, let's say, and you multiply that by the length. That's where this value would come from. And then I'm going to be looking at the impact on an adjacent feeder, because if you're a customer on the same circuit as the fault, you're probably out of luck anyways. But if you're on the adjacent circuit, then you're not going to see an interruption, but you're going to see a sag. So I have a bus here called VP that's marked with the voltage VPCC. That stands for point of common coupling. And basically, this is the point of common coupling between where the fault's going to occur and where a customer on an adjacent feeder is going to have an impact. And so this is the unfaulted branch, and I'm wanting to know what the voltage is here. Now, in this methodology, if I have a customer on this second feeder, I'm going to neglect the voltage drop due to load, because that's going to be negligible compared to the voltage sag I'm going to have compared to the fault. So really, all I'm really doing in this case is I'm solving for IF. This fault current is going to be the substation voltage divided by the substation plus the line impedance. And then if I want to calculate the voltage at the point of common coupling, I just take the substation voltage, I subtract off the drop across the substation impedance. In a way, you can think about this as kind of being a voltage divider in a way. So anyway, as far as the line impedance calculations, we've done this quite a bit before in class. You're going to have some underground line sections as well, but mostly we're looking at the fault current that's due to faults that are going to be on the backbone of the circuit. And this is going to be probably more aligned with having the overhead. And we've done calculations along these lines where we're calculating the positive sequence impedance. And so for different conductor sizes, I've got some typical values that I've calculated in the past. And you'll note in here that as you get into the smaller sizes, then what you start to see is you start to see this resistance go up. The line reactance doesn't change as much because the line reactance is more of the function of the spacing. That's more of the construction. So that's more of a function of the distance between the conductors, but the resistance goes up as the wire size goes down. And so if we were going to do these calculations for a typical circuit, let's suppose we have a monitor at the feeder head. This could maybe be what we get from the top of feeder relay. And let's suppose we had 3 different types of constructions here. And I've got the line lengths I'm assuming for each type. Then basically what we would do is we multiply by the line length, we'd get an impedance for each of these sections here. And one thing you see on typical distribution circuits is typically as you get further away from the substation, the wire size goes down. The wire size goes down because we have less load. The further we get from the substation, the less load we have. And so you typically see this telescoping effect where we have the higher line ratings at the top, then the line ratings drop off, and they finally drop down where they get kind of small toward the edges of the circuit. Now, in this case, if I'm looking at faults at these different points at bus 1, 2, 3, 4, Then at bus 1, the fault current's only limited by the substation source. So if the substation source in this case has this net impedance here, then basically this current's going to be really high. And 6,000 amps would be a typical value of current we could even see at a substation. Maybe it even gets up to 10,000 amps, but it's going to be, typically above like 4,000 amps. Then when we get to like location number 2, where we have the length of the 336, then we factor that into our impedance. And what we get is we get a smaller fault current. Now, when I start calculating this voltage here, if I have the fault right at the bus, the voltage goes to 0. If I have the large amount of current, what's going to happen is I'm going to get a drop across the substation, which in this case is going to give me 63% of the nominal voltage at this particular point for fault at bus number 2. And then if I'm looking at a fault at bus number 3, then the current's going to drop down some more, and then the voltage sag is at this particular bus that's feeding these other feeders, it's only going to drop down to 81%. And if I get way at the end, it only drops down 5% to 95%. Okay, so the further you get away from the substation, the less the fault current, and the less sag you'll actually have in adjacent feeders as a result of that. So what really kind of hurts us is being a customer on adjacent circuit are the faults that are closer to the substation, because those draw the most current and those are going to cause the most voltage sag. This shows an actual recording taken at a customer site, and this has been pre-unitized. And again, a lot of these sags that we see are between 0.5 and 30 cycles in duration. They're sags associated with the time it takes to clear the fault. Now, in this case right here, we can see this fault didn't last very long. Basically, this fault only lasted, went from 0.02 to about 0.055. So that's about maybe 2 electrical cycles. And this would be about the time it would take to clear a fault with the fuse, right? And so what you see at the customer side is you see this voltage sag down. And this is what we're worried about right here again, is that we're worried about what's going to be the duration of this, and we're worried about how far down it's going to sag. But this shows a typical sag that's due to a protection event, say like a fuse clearing the fault. So as far as looking at the impact of a fault on power quality, what's this going to be determined by? It kind of depends on how the system protection and coordination is set up. What kind of philosophy do we use for like syncing in the fuses with the breakers, and how many reclosers do we have out there? Do we use fuse savings or not, right? So you have to look at how the protection coordination is designed. You have to look at the types of disturbances that would likely occur. And you got to figure out, first of all, is that disturbance going to cause an interruption? So is it going to cause like a breaker to operate to try to clear, say, like a temporary fault? You got to be looking at whether, depending on the fault location, whether that would be just a momentary outage or maybe even a sustained outage. And then you got to look to see to what extent can this disturbance cause like a voltage deviation and cause a voltage sag. So basically, you almost have to like draw the system out and kind of conceptualize how the protection operate, kind of similar to what we had to do when we were doing the reliability, safety calculations. So I'm going to kind of walk through some different scenarios of faults on distribution just to kind of show you what's going to occur in each situation. And this was some material I'd put together for a short course for industrial customers, so they can kind of understand why they're seeing the types of disturbances they're seeing. So here's this 2-feeder circuit, and I've got the possible fault locations at locations A through F in this case. The feeder circuit breakers at the top of the feeder, they would be set up where you didn't have fuse savings, where the downstream line reclosers may or may not, depending on whether you had slow or fast downstream fuses. Again, typically at the top of the feeder, you usually have no hope of fuse savings. And so typically we just try to clear a fault in the lateral as fast as we could with a fast fuse. However, below a line recloser, we have a chance of clearing a temporary fault. So we use slower fuses below the reclosers. And I'm be looking at it from the perspective of having a monitor at the top of the feeder, as well as a monitor on this customer on the lower left-hand corner here. And so you could think about this as being maybe a relay or like a power quality monitoring box. And the customer, they may have like a Dranitz or some sort of other industrial power quality at their plant entrance. So let's take a look at fault scenario A. Let's look at this scenario here. What's going to happen in this case? Well, let's suppose I had a fault here. What's going to happen? Well, what I'm going to see, obviously, is I'm going to see a high flow of current, but this fuse is going to clear really fast, maybe in a fraction of a cycle. And so it's not going to cause this breaker to operate. This breaker is going to hang in there. But what it's going to cause, since I have a high flow of current, is we're going to see a voltage sag. And so what this customer is going to see is it's going to see a voltage sag, about the same amount of sag as that feeder monitor, because we're assuming this voltage drop across here is basically zero on this non-faulted feeder. So what's this going to look like? Well, if I had monitoring at the top of the circuit, and these are some recorded waveforms, we see this really high current is monitored from the substation. This is the current going through the fuse, but the fuse clears this really fast. And so it jumps up to a really high value, but doesn't jump up too long. And this is going to cause a little bit of a voltage deviation on the unfaulted section of the circuit. So it's monitored from the top of the feeder. If I take the substation impedance and multiply it by this current, then this amount of deviation is what that corresponds to. So it's not really much of a disturbance as seen by this customer monitor or by this top of feeder monitor. What would happen if we're at scenario B and if I have a fault right here? Well, what's going to happen in this case is if this is a temporary fault, it could be cleared by the operation of that line recloser. And so what's going to happen is this line recloser is going to be set up on its slow curve, on its fast curve. It's going to operate first, try to clear the fault. After a while, if this line recloser can't clear it, then it's going to switch to its other curve, and what it's going to do, it's going to cause this fuse to operate. And so this is a fuse savings case in this particular instance. If this fuse were to blow, then anybody obviously below here would be outage. But keep in mind that as this recloser operates, then any customers below that recloser would actually see momentary interruptions. And so as this recloser tries to clear the fault, maybe after the first time it doesn't work, it might try a second time. We're going to get a large amount of current flow from the source to this point of the fault. And then that's going to cause a sag at the feeder monitor, which is also going to be seen by this customer monitor. This shows some recorded waveforms at the top of the feeder. And you could see that pre-fault, we had a normal amount of load current here. And then during the fault, this current jumps up to a high value. And so what happens is the recloser operates open, and you see that the load level drops. This is because all the load below the recloser is disconnected. And in this case, we don't reclose for another couple seconds. So this is kind of a long delay. So that's not too good, obviously, for a customer below that recloser. But as far as a customer on the adjacent circuit, on the non-faulted circuit, all they're going to see here is we're going to see this little glitch in the voltage do this particular operation. Now, this shows the reclosing occurring here, and the load gets picked up again. This shows the reclosing occurring and the fault's gone. But if the fault were there again, then it would jump up to a high value and you'd go through this whole cycle again. And so that sequence, the sequence where you have the fault and you open, sometimes that's referred to as a shot. And reclosers could be set up for maybe 1, 2, or 3 shots where they'll try to clear the fault. This shows what a voltage sag would look like for an uninterrupted customer. It doesn't exactly match up to the previous case. This is actually a different case, but it basically shows what happens on the adjacent circuit. And this is a case where you had a pretty deep sag. So the slope right here, this is kind of due to the signal processing, calculating the RMS value. But what the time domain waveform actually looks like looks like this right here. It's really kind of distorted looking. And then even when we kind of get into steady state a little bit, it's not even a sine wave anymore. And this is because if you have a fault's not actually a perfect zero impedance. A fault's not even a perfect low impedance. A lot of these faults have kind of time varying resistance. And so because of that, the current gets pretty erratic, and as a result, the voltage can get kind of erratic. So it's not a nice sine waveform that that you see on the unfaulted phase necessarily. So fault scenario C, this is a case where you have fuse to fuse coordination. If these fuses are coordinated, this fuse right here should blow. So we'll see a little bit of a sag on the rest of the circuit right here, and we'll just outage people below this point. And then fault scenario D, if the fault's on here, high up near the substation, this is going to cause a lot of current flow. What this customer monitor is going to see an extreme drop in voltage, but it even gets kind of worse because once that top of feeder relay sees that fault, it's going to go through a reclosing cycle. Typically, it's going to be set up where it's going to open up and then try to close. So at first, what's going to happen, this customer monitor is going to see a sag, and then it's going to see a momentary outage. But then if this fault stays permanent, we get a sustained outage anyway. And so anyway, this is going to be kind of a worst case as far as this customer is concerned. Maybe the fault's going to get cleared, but the customer is going to see a lot of power quality events as a result of that particular type of operation. These station breakers, they tend to trip open pretty fast and tend to reclose pretty fast, but there's still going to be delays on order of cycles in this case. And we'll go through a worked example with some numbers in this case. Fault scenario E, this is below a line recloser. And so what's going to happen is the recloser is going to sense the fault and it's going to try to clear it. What's going to happen is that it's going to operate open, and what that's going to cause right here, this is going to cause a momentary interruption. It may take about 20 cycles or so, or maybe even up to 2 to 5 seconds, depending how this recloser is set up, for that service to be restored. So this is another bad event for this customer. If you have a fault right here, then this recloser is going to try to operate in order to clear that fault. If the fault's going to be permanent, then also this recloser is going to lock out. So this is another sort of bad case. Anytime you have a fault on the same circuit as your critical customer, there's usually not any really good outcomes in that case. They're going to see sags, they're going to see momentary interruptions, and they may even see like a sustained interruption. And then the F scenario is where you have a slow tap fuse in this case, and you try to do fuse savings. Now, what happens in this case is that the recloser is going to operate first because it's going to try to save this fuse. And what this means is this customer right here is going to see momentary outages. And maybe this fault could be cleared after a couple shots. But what this means is that customer is going to see a couple very momentary interruptions. Depending on that customer's processes, that might be the same as a sustained outage, because that can mess up their processes. And so let's suppose you have a mixed use circuit and you've got these industrial customers or industrial customer, and you're next to a residential feeder, or you have a number of residential feeders. And let's suppose these feeders have a lot of issues with trees. Well, if you try to do fuse savings in here, this critical customer is going to be subjected to a lot of momentary interruptions. So what are you going to do about something like that? Well, this is where you have to kind of look at the trade-offs. So in some cases, what the utilities would do is they may disable fuse savings. What they could do is they could put a faster fuse here, and you wouldn't have fuse savings on the circuits that have a lot of trees. You would maybe put the fast fuses on those circuits. Maybe on those circuits that didn't get many events, you may try to do fuse savings, but this is where you might either disable fuse savings or use a hybrid scheme where you only do maybe selected laterals for the fuse savings, so you don't have all these interruptions on this industrial customer. So anyway, when we talk about these momentary interruptions, let's suppose this is a 2-second case right here, where you have the upstream breaker operate. Basically, if you looked at this on an RMS meter, the voltage would essentially go to 0 until you could restore service again, right? What's kind of interesting, and the time scales aren't set up the same, but what's kind of interesting, if you look at the voltage at the customer in detail in the time domain, you actually see a little bit of voltage and it kind of drops off, kind of tails off. This is what's referred to as spin down. And if industrial customer has a lot of motors, what happens is when they get isolated from the grid, the motors actually go into generation mode, and as they're spinning down, actually create a voltage at the bus, but that voltage is kind of low and it decays out pretty fast. But that's a spin down voltage. So we talked about this before. Like if you're an industrial customer, you'll typically want to have some sort of monitoring of your voltages. This is another type of meter that was kind of popular, the Duranit's PX5. This is a portable device. You can rent these sort of devices out. It comes with some high frequency leads for taking voltage and current measurements, and it could capture these types of waveforms. And so if you're having some issues, you can actually buy one of these devices or maybe rent it out for a period of time. The higher end meters, what we call C&I, commercial and industrial metering, also has some limited voltage power quality event monitoring capability. And so this is a General Electric KB2C. This is used by a lot of meter companies. They actually install their communications in here and actually sell this as part of their meter offerings. But this would be a device you'd use at your higher end commercial industrial customers. And you could also program this device right here to capture this type of information as well. Not in the same granularity as a Duranit's, but it would give you some indication that these events are occurring and at what quantities. One other thing I want to mention too is that when you do have a device capture this information, they all have their own proprietary data storage formats. But a lot of times you can dump this into a standard sort of a waveform file that's referred to as a Comtrade data format. And the IEEE standard for this is C37.111. And it basically specifies a standard for capturing power quality information where you can exchange it between different entities. And so this will have a header file. Now, in this case, this came from a simulation, but it'll have a header file about when it was generated. It'll have information about the channels that you capture. And then the data, there's an ASCII format, there's a binary format. This is ASCII format. And what it does is it captures, the time step difference between the points. It captures like voltage and current information. And what you could do if you have a Comtrade file, then they have these Comtrade file viewers. And so let's suppose you had like a Schweitzer relay and you have a oscillographic waveform, and it's kind of in a format that's native to the Schweitzer. You could view that with the Schweitzer waveform viewing tool, but if you wanted to give that to somebody else, you can convert that to Comtrade. And then a lot of people would have the ability of actually viewing that file. So anyway, let's stop here, and then in the next segment, we'll do a numerical example on these voltage sag calculations.